Uh, so thanks so much for giving me this opportunity to introduce some preliminary results of this new model, AWIESM equipped with water isotopes. So the outline of this work, I will introduce the model and our experimental design, and I will show the model's performance in presenting the pre-industrial isotope field and compare it with the LGM state and some interglacial climate state, finally give some conclusions and outlook. So I will start with this model description. So basically, we have the ACAM6 as our atmospheric model, which also include land surface model JSPAR. And the isotope process has been implemented into all of the relevant components of this water cycle, as shown in this plot. And for the ocean side, we have AWIESM 2.1 as the model, and in the ocean, the tracers, the isotope is treated as passive tracers, and the fractionation could be occur during the formation of sea ice. So there are several highlights of this new model, and here I will give two examples. And the first is the use of nonlinear phase surface formulation. So in the left side, you see a traditional linear phase surface, which is used widely by most of the Earth system models. So basically, we have this depth of layers, which is fixed at a certain volume. For example, you can have 5 meters for the first layer, 10 meters for the second, and third layer, and so on. Whenever there is fresh water cannot alter the volume of that grid cell because the depth is actually fixed. So in this way, we have to implement a virtual salinity flux so that the salinity in that grid cell could be altered. And in the right side, you see what is used in our model, which is called the nonlinear phase surface formulation. So in this way, the depth of the layer could be changed with through time and space. So the freshwater flux can directly affect the volume of the layer and thus alternate the salinity. This is actually what happened in the real world. So with this nonlinear phase surface approach, we are able to describe a more realistic ocean process. So another highlight of the model as shown here in this plot is the use of high resolution. I zoom in a small area in the coast region. As you can see here, we have many small triangles in the coast area. Yes, we have refined the resolution over the tropical belt and also in all of the coastal area with a resolution of about 30 to 50 kilometers. If you go further to the north, so for the Antarctic region, north of 50°, you see here the triangles are even smaller and with a resolution of like 12 to 15 kilometers. So with this state-of-the-art model, we are able to simulate several experiments. So the first is the PI conference state, which are used for the model validation, also for serves as a reference state for the other paleoclimate simulation to compare with. Then the second very important cold climate LGM simulation, which is basically the 21K based on sea ice sheet reconstruction from Galactic 1D. And in addition, we perform several interglacial warm period like the mid-Holocene, which is 6K, early Holocene 8.2K, and the last interglacial, which is 127K. I will focus on two variables. The first is delta ATO in precipitation, and second, the delta ATO in seawater. So for the model result, we'll first start with the PI validation. So here I show the delta ATO in precipitation as simulated in our PI simulation. Basically, we capture all of the typical characteristic of the global map of delta ATO in precipitation very correctly. First is the temperature effect, which you go from the tropical oceans to the high latitude. You get this delta ATO more and more depleted. And the most depleted delta ATO you can find in the Antarctic and followed by the Greenland. And another pattern is from the coastal area. If you go from coastal to the inland, you get this delta ATO more and more depleted. So this is called like a continental effect. So we here I compare our modeling to the global network measurements from GNIP and some ice core measurements from Greenland and Antarctic. So you can see from the colors in the small circles and the background colors, they are very similar. For a more accurate comparison, I plot the modeled value against this measurement value for all of the measurement locations in this scatter plot. So we see that they are very close to the reference line, indicate a very good model data match, despite a little bit bias over the Antarctic core, where our model result is a little bit less depleted as compared to the measurements. So in the next slide, I show the delta APOE surface seawater for PI. Here I have chosen two different reconstruction data. The first is a global network from GISS, as you see these small dots. And the other one is a more recent product by Brett Cross 3 years ago. This is basically a simulation product based on both proxies and modeling. So we capture the enrichment of delta APOE in seawater in the tropical oceans and the subtropical oceans, especially for North Atlantic, the Mediterranean River, Sea, and the Red Sea. So they are due to the net export of fresh water and the net evaporation flux. And the depletion of seawater you can find here in the Arctic region and followed by the South Ocean. So if we compare our model result with this, with two different data sets, you might find there is the pattern similar pattern. They are very similar, and this indicated our model result is in line at least with the GISS and this more recent the estimation product. So we go to the interior of the ocean. I calculated the zoonomy of delta APOE at seawater for two different ocean basins. The first is the Atlantic, as shown in the upper plot, and the second for the Pacific, shown in the lower part. So for the Atlantic region, we get the enrichment of delta APO of seawater, which is limited constraint over the top layers for the South Atlantic and the North Atlantic. And then because of the water advection, diffusing, or the mixing of seawater, this signal can be further transported to the bottom water and then to the south. And for the Pacific section, because the mixed layer depth in this section is much shallower as compared to the Atlantic, so we have this enrichment only constraint on the surface of on the upper layers, like from 0 to maybe 800 meters. So leaving the rest of the ocean a little bit more depleted in seawater in delta APO. And if we compare our model result with again with this simulation reconstruction from Bycross, you see very, very similar patterns, despite a little bit bias discrepancies in the absolute values, but actually we capture the pattern and the gradient very correctly. So next, I would like to talk about our LGM simulations, and first to introduce some basic mean climate changes between LGM and PI. So we saw here the first, the left side, the surface air temperature, is the middle, the precipitation, and in the right, the sea surface temperature against some reconstruction from pollen data, and for the SST is from a multiple archive reconstructions for the SST. And basically we have the global cooling for LGM due to a reduction in greenhouse gas and the presence of ice sheet over the North Hemisphere. And the second thing is the dryness over most of the global pattern, especially for the North Hemisphere monsoon patterns, monsoon regions with a local wetness located here in the south part of North America. So these are in line with the proxy records and also in line with most of the PMIP model example simulations. So let's go to the isotope fields. So first is delta APOE precipitation. So we have this depleted delta APOE precipitation, which is simulated by the LGM simulation here for the ice sheet region, like the Laurentide ice sheet, the European ice sheet, the Antarctic, and the Greenland. We are aware of that in our LGM simulation because we have a anomaly of southerly wind over North Atlantic, which blow to the north. So which brings some kind of warm water, which is accumulated over the Baffin Bay here. So we have a warming bias over Baffin Bay, and this will further affect the isotope fractionation over the Greenland. So on the Greenland, we have a bias. So our simulated isotope is much less depleted as compared to the Greenland ice core. So we are still fighting on this by introducing new improved boundary conditions or by introducing the iceberg module inside. So we are on the way to make the model more perfect. So the next is the delta in surface water. Here I plot this one against the a recent compilation of planktonic from manipulated records from Lucas Yonkers last year. So basically we see a very complex pattern here, but we can conclude that there is good model data agreement over most of the ocean basins globally. So for example, the tropical Atlantic and North Atlantic, this eastern part of Pacific, and the coastal area of Australia, the South Ocean, and the northern part of Red Sea, they are all in line with the foreign military records, but we are also notice there is a little bit data mismatch, which is happen in the South Atlantic. So basically, our simulated data here is much too less enriched in the delta 18O as compared to what we show here from the foreign military records. So to going deeper to the ocean side, we might we find that for the Atlantic section, here we again compared our model results with the basic foreign military records. And for the Atlantic section, in the lower part from 2,000 meters, and we are agree quite well with the values, like from with the anomaly being 1.4 to 1.6 per mil for the anomaly between LGM and PI. And for the Pacific, this is 1.3 to 1.4 per mil, which is also shown by both the model result and by the foreign military data. But we are also notice that there is some very sparse point, which is located in the Atlantic section from up there to 2000. Some of them, you see these very, very red points. They are with a value like more than 2 per mil, and our model fails to capture this very, very large anomaly between LGM and PI. So I will spend 2 more slides on the results of the interglacial simulation. I didn't have time to find enough proxy to compare, so I will basically only focus on the pure modeling stuff. So first is the surface air temperature. We have increased salinity as simulated in the interglacials as compared to PI, which is indicated by the cooling of winter, or boreal winter in BGF, and the warming over GGA, especially over the northern hemisphere continents. And for the early Holocene, we have, as we have still a remaining sea ice sheet around this Hudson Bay, so which is dominated by a cooling all year round. So, and the next is delta 18OE precipitation. So a very common pattern shared by these interglacials is the enrichment in delta 18OE precipitation over the Greenland, Arctic, and the Antarctic. But with different magnitudes, such as such signal is the most pronounced in last interglacial, but the least pronounced in 6K. So another pattern here we show is the depletion of delta 18OE precipitation over North Africa and Europe and South Asia, and some part in the North America. This is because of the northward shift of RTCZ in a warmer climate. So which bring more precipitation to the North hemisphere monsoon regions. So come to a conclusion. First of all, we are very confident in our model's performance in presenting the pre-industrial isotope fields. And then we found that our LGM simulation very nicely matched most of the reconstructions, various reconstructions from like anti-ice cores or from medieval records. But we notice a large bias over Greenland ice cores, but this is not due to an error in the isotope physics, but due to something happening in the climate physics. So the next step will be a transient Holocene simulation, as well as the MS3 simulation or interglacial cycles, which will be probably finished by the end of next year. So finally, I would like to give my special thanks to my supervisor, Martin Werner, who has guided me through all of these processes, and to Alexander, who answered me a lot of questions and helped me on the ICOM 6 model at the beginning of my work when I was stupid, and to Yuchen, who has implemented all of the ocean isotope tracers in FASM 2, and to Jonkers, who gave me a lot of the foreign municipal records from his compilation. So finally, we would like to share our data to make our data public, but before the data will finally be summarized or standardized, which might take a lot of times, like 1 year or 2 years. If anyone would like to have the data beforehand, please just feel free to contact either me or my supervisor, Martin Werner. So thanks for your attention.